So today we have our fifth recitation of the semester, and today we're going to be talking about Bellman's principle of optimality, how we can use this and a method for dynamic programming to solve our LQR problems. And then outside of the class of LQR, we're going to talk more about MPC, which is probably the biggest takeaway from this class. And when people think of optimal control in practice, at least in a research setting in robotics, we're often talking about MPC. And then I have some code for like a simple version using a quadrotor. So with that, we'll get started on Bellman. And all the Bellman stuff, you're going to see it a few times. It really does, for some reason, take a few times of seeing it to actually understand it. So if you've seen this before, hang with me, but it really is super important. So I'm going to draw out what Bellman's principle of optimality is in terms of what it looks like graphically. So imagine if I had a 2D state space like this. This is, x1, x2. If I have a 2D state space and I have some goal right here. Now imagine I have a trajectory that I tell you is optimal. So I say if I start here, my optimal trajectory to get to the goal is going to do this. I'll put an arrow. So the whole idea of Bellman's principle of optimality is that subsections of an optimal trajectory are still optimal. And it's so obvious that it almost confuses people because they assume that they're not quite hearing it right. But all this means is that if I tell you that by starting here, the best way for me to get to the goal is by doing this, that means that if I were to drop you right here, that means the best way to get from here to the goal is following the same path. If you think about this in terms of like a contradiction, imagine if there was a cheaper route to get to the goal like this, why didn't we take that in the first place? So any sub trajectory of this thing from here is also optimal. Say we start from here, also optimal. It doesn't matter where we start in this trajectory. It is always the best way to get from our current position to the end, assuming that this black trajectory is the optimal trajectory. Now, I guess maybe a more common way to think about this is imagine if I was flying places and I wanted to fly from, I want to fly from Pittsburgh to Tokyo or something, and I had to make a bunch of different hops. Imagine if there was like, okay, the best way to get there is to go from Pittsburgh to LAX to Tokyo. But then it turns out that like, from LAX to Tokyo, there's actually a better way to get there. Well, you would have taken that in the first place. So any sub trajectory within your larger optimal trajectory is also going to be optimal. It turns out that the reason that Bellman stuff is just so cool is because this is such a simple idea. And once you sit there and think about it for a few minutes, like it makes total sense. And this is all you need to back out some pretty awesome solutions to some really difficult problems. So if we take this assumption, say that you've thought about it, you understand it, for an optimal trajectory, any sub-trajectory, so if I start at the middle of it, my best way to go is still going here. If there's a better way, I would have taken it in the first place. Once I had this assumption, I can now start from the end and work backwards. So that means is I can start at the goal. I can move kind of, a step away from the goal and say, what's the best way to get here? I can move a step away. What's the best way to get from there? And I can build up the best way to get there by working backwards from the goal to the start. And this is where we get into dynamic programming. And this is a classic like research buzzword. So the origin of dynamic programming was like Richard Bellman basically wanted more funding from the government, specifically in the world of defense. And he wanted to make it sound like super flashy and cool. So it's called dynamic programming. And this is at the time when like linear programming was becoming very popular. It's funny how like these things get named, partially because it's an appropriate name, but also partially because they have to be like some salesmanship to get people to pay for these ideas. So the idea of dynamic programming is we just start from the end, start from goal, and we're going to work backwards. And then so we start from the goal. We're going to work backwards, assuming that every backward step that we take is optimal. So if I start here at this goal, I'll take a step back and like, what's the best way to get from this step here? And then do the same thing, and I keep going. And you're always going to be optimal if you do this. The issue is that this is cursed by the curse of dimensionality. So it's very difficult to solve these problems when we have a large state space or a large control space. So it really only works for simple stuff. Turns out that simple stuff means linear dynamics is one of those things that works really well with this. And that's, we love using linearized models. We sometimes have linear models, and all these things make dynamic programming with linear models work super well. And with that, we can get into how we get the LQR problem. So let's talk about, and this is something that we went through last time, is we talked about finite horizon or time variant LQR. And if you remember what this problem looked like, this was min x 1 to n, u 1 to n minus 1. And this was from 1 to n minus 1, xi, ui. And then we have a terminal cost, xn, qn, xn. Then for our constraints, we have our linear dynamics. We said that x phi plus 1 equals a xi plus b ui. And this is for I equals 1, 2, and minus 1. And then we have our initial condition that just says x1 must be equal to x, our initial condition. So we start off this problem with a set spot in the state space. So this was the problem that we went over last time. We can solve this. We have all these great methods to solve it. Now we're going to talk about how we actually get one of those methods, arguably the most popular method. So from here, if we think about how simple this problem is, I have a stage cost. Stage cost, and then terminal cost. And now let's relate this back to dynamic programming. So the idea of dynamic programming is that I have a value function. So the value function of x is optimal cost to go from x. And what that means, again, it's very simple, but it's so simple it's almost confusing. This means that if I drop you somewhere, my value function at there is basically how much it would cost if I act optimally and go all the way back to the goal. So if I drop myself anywhere in the state space, this value function v should tell you what the cost you will incur if you act optimally from there until the end. So if I drop you here, then that cost to go is just the cost of the full trajectory. If I drop you here, the cost of this. And if I've solved this value function, you can think about how important this is. If I know the value function for everything, then I can know if I drop you here, what is the price of the cheapest way to get to the goal? If I drop you here, same thing. So the idea is that this thing is super important. This is the optimal. So this is the lowest cost to go that you could get from any point that you drop X. And this is really hard to get. If we knew this, a lot of these problems would be solved. And it turns out that for LQR, we are going to figure out a way to actually know this. So now when we do solution via dynamic programming, what we're going to start with is what is the cost to go at the final time step? So I'll just do a new page. Riccati via dynamic programming. So what is the value function at the last time step? This is us just saying value function at n. And if you look at our cost, what cost so this is our full cost. We have a stage cost and a terminal cost. If I'm at the last time step, remember in dynamic programming, I start from the goal and I work backwards. if I'm at the last time step, what is the minimum cost I can incur? So it's just the terminal cost. So again, this would be like me starting right here. If I start at the goal, what is the terminal, what is the cost I can incur if I act optimally? So the minimum cost is going to be the terminal cost. So this means that our value function is x transpose qn x. And this leads us to our next introduction of notation, which is the action value function. And now you'll see Q or S. Zach likes to use S in this class, so I'll use S. So S of X and U, this is just the, this is one element of the stage cost. Then plus V of whatever our dynamics function is. So we'll assume linear dynamics for this. Now, these two things kind of form the basis of both a lot of control stuff, but as well as also lots of RL stuff. So our value function, this tells us what is the cost to go from that point if I act optimally. The action value function, this tells you there's no assumption of optimality. It's just here's my current cost and value function if I act optimal. But the current cost, I can do whatever. So when we think about when we want to define what is the value function for the time step of n minus 1, we get v n minus 1 of x equals min u and this is super important. So like with just this right here, you can get a basic understanding of what's going on. Here's our value function. It starts out for this final time step. We're going to talk about what this turns into in the time steps that precede it. But here's our final time step. Here's our action value function. Give these names. Value, action value. Now from here, let's just turn the crank and let's see what we get. So if we start with this as our last value function, and I want to find Vn minus 1, here's all I have to do. I have to do Vn minus 1 x equals min u. And the first thing we have here is our stage cost. This is just x transpose q x plus u transpose ru. And this is our stage cost for just this one time step. And then I get my value function at the next time step, which is plus Vn ax plus bu. Now, what do we know about this is that our Vn is actually just a quadratic. So our Vn is just a quadratic right here. So that means that I can just copy all this. And now let's make one quick assumption. So before we got started on this, let's just assume something. And if it turns out to not be true, then we can change it. But let's just assume it's true. So I'm going to assume a quadratic value function that looks like this. V of k x equals x transpose s k x. So what does that mean? Well, if I just line this up with what my last value function is, this means that my s of n is just q of n. So if my s of n is just q, and then I'll go ahead and just write s right here, just to keep things nice and general. So S of n equals Q of n. Okay. So now this I said that my value function f or v n minus 1 x equals the minimization of this right here. Now this is super, super easy for us to minimize. And how do we do that? We just take the gradient of this. So gradient of, so this is, remember, this is Q n minus 1 xu. So if I take gradient with respect to u of Q n minus 1, what I get is RU, and then or I get 2 RU, and then 2 B transpose S, and uh, so if I take the gradient with respect to U, I get this right here. And then I can just go ahead and solve this by just doing, I can take out the 2's, so I get um, R plus B transpose SN B U equals negative B transpose SN AX. Now, if I go ahead and solve for U, what I get here is I get U equals negative R plus B transpose SN B inverse B transpose SN A X. And now it should be clicking that, like, what just happened here is actually pretty cool. So what I get is I get that U is just a straight function of X, and it's just a linear, it's just a matrix times. So this will call us our gain K. And this actually tells us something pretty cool. So this means that our control input at n minus 1, so I'll write this out. So U at n minus 1 equals negative R plus B transpose Sn inverse B transpose Sn A X. And this is, so do a quick recap of what we just did. So we started out by saying that our value function at the last time step is just Q, or X transpose Q and X. We say, let's go ahead and assume that this is quadratic. So we're just going to say that our value function for every time step will just be V of K of X equals X transpose S of K and X. This means that, if we line up this and this, we see that S of N is just Q of N. And then if I go ahead and I take the value function at n minus 1, so I do my dynamic programming, I take one backwards step. What I see is that I have, a stage cost, and then I have my value function at the next time step, which is just a nice quadratic. So I go and I plug everything in, I get this. I take the minimum of this over U, and this gives me this right here. And then so I've now solved this problem, but I don't know what the value function is because I have to plug this back in. So if I take this and I plug it back in, if I say that U of n minus 1 equals negative K X n minus 1, and I plug this back in, so plug. I plug this back in here. What I get is I get V n minus 1 X equals X transpose QX. And then the next term is U transpose, so I'll write it all out and then I'll plug it in. So plus U transpose RU plus AX plus BU Sn. So now if I plug in my u equals negative kx, I get x transpose qx plus x transpose k transpose r kx. And then I get a minus bk x transpose Sn a minus bk x. And what we see is that all these terms are quadratic. So our value function we assumed was quadratic for our last time step. Now it turns out that if we go and plug everything in, our n minus 1 is also quadratic. I'm just x transpose, and I got a lot of terms here. I have a q, I have k transpose rk, and then I have a minus bk transpose Sn a minus bk. So V and this is my value function at the second to last time step. So again, another quadratic. What does this mean? This means that I'll just take this term out, and this will be S n minus 1. So this is how we do the full Ricardo regression. We can keep doing this. We started out with the last time step to the second last, but nothing in here was specific to the last time step. All I know is that I just had this nice recursion where I have a function that tells me what my control input would be as a function of the state, and I can just plug that back in. And the actual value of the state drops out, and the value quadratic, it just gives me this S right here. And this gives us the Riccati recursion. So we initialize with Sn equals Qn, and then for I equals n minus 1, n minus 2, back to 1, I get K of I equals R plus B transpose S I plus 1, B inverse B transpose S I plus 1, A. So this gives us our gain K, and then we update our value function Si, the quadratic term in our value function, just becomes Q plus Ki transpose R Ki plus A minus B Ki. And this is it. So what I just went over, I'll do a quick sweep of it one more time. We assume that our value function for our problem was quadratic. We just assume that. And then if it turned out to not to be true, then we would have to just change it. But when we assume our value function is quadratic, this tells us the optimal cost to go at a given point. So we look at it for our last time step, where the only cost left in our original cost function was the terminal cost. So we say, okay, our quadratic term is just Qn. And then we want to find the value function at the n minus 1 time step. This means we just minimize this function right here, which is our stage cost plus our value function. And if I go and I plug in everything for linear dynamics, what this means is that Vn minus 1 is the minimum over u of our stage cost plus our value function at the next time step. And because we already know what this is Sn equals Qn. I know what my value function is at the last time step. I just go ahead and plug that in. So now value function at n minus 1 is the minimum over u of our stage cost, and the value function at the end time step. And then this red part here, I'm just turning the crank. I'm just taking the gradient of this thing with respect to u, which gives me the minimizing argument. So this tells me what u is. And then with that, I now know the minimum value itself. Because remember, this is min and not argmin. So in order to find the minimum, I have to find the argument that minimizes it, and then see what the value is at that minimum. So I take that u and I plug it back in, and I have this, u equals negative kx I plug this back into my Vn minus 1, which was this. And then I add in my u equals negative kx. So this turns into this turns into this and this. And then I see that I recover another quadratic. So the assumption I made at the start turned out to be a good one because I assumed the value function would be quadratic. And I just did all this math and I turned the crank. And now I look at my value function at the n minus 1 time step. And I see that it's once again quadratic. And here's my expression for what this term is. And so we showed this for the last 2 time steps, but you can just keep going, keep going, keep going. And we developed like a recursion here. And so this is the full recursion where we initialize our value function quadratic at the terminal cost matrix. And then we just iterate from n minus 1 down to 1. And at each time we solve for a gain k, and then this value function quadratic here. And this is how we solve finite horizon LQR. Now I can do time varying LQR, just where A and B change over time, just by adding in the correct indices for A. So I'll do, we can solve
Quick question, if we could go back up top. Right, so here where you took the gradient of Q, what's the difference between this Q and minus 1 and the Q inside that min?
Sorry, I meant to say S. So Zach calls this S for action value function. So this is wrong. I need to say this is S. And then,
Okay. Okay, this is.
sorry. So this is
And
this is exactly why Zach uses S and not Q. Most people use,
right.
but because we're using Q in our cost function, it's just kind of confusing. But S, so
And
V is our value function and S is our action value function.
okay. And that Sn inside the min is the same value function, but um at the next time step.
Yep. So what
Okay.
this is our stage cost at the n minus 1 time step, and then our value function at the n time step. And this is true for everything. Our value function will always be, as you saw right here. So this can be just k. So the value function at k is the minimum of this, which is minimum u terminal cost at time step k, xu, then terminal cost, or sorry, value function at k plus 1, and then, which is, so this is our, like, this is Bellman's principle of optimality right here. This is the Bellman equation.
So,
And
oh, sorry.
go ahead, go ahead.
Kevin, if you just go back to what you wrote now, does that actually mean the first term, the stage cost is the cost for you to go from the current point to the optimal trajectory, and then the V of X, V of the rest of the cost is the cost to traverse the trajectory. Is that what it means?
So basically what it means is that this is the cost that I will incur immediately between time step k and k plus 1. And then if I'm at time step k plus 1, this value function tells me the minimum cost from that state. So, and this is why we have to minimize over it, because imagine if I had, they'll often do this for a grid world example. So imagine if I had, so they love doing the grid world stuff. And so what you'll see is that you'll see this grid. And the idea is that they all have different costs associated with them and different, so imagine if every grid here had like a 2, 3, 1, 3, 2, and then this was goal. What the value function tells me is that from this state, what is the cheapest way to get to the goal? So in this case, it'd be going here and here. From here, it'd be here, here, here. And then from here, it'd be here, here, here. Now, what we're talking about with the value function is that assume that I have a cost that is the cost from me to go to here, or me to go to here, or me to go to here. This is that terminal cost. And then the value function tells me once I'm here, here, or here, what is the cheapest way to get there? So if I know that, if I know the value function, then I just want to get to the best place possible. I want to, given my terminal cost, how much it costs me to go from A to B. I want to get to B, which has the minimum cost optimally to get to the goal. Does that make sense?
Yeah, actually.
And I'll link when I post this recitation, I'll link a video to the grid world stuff for dynamic programming, which is the most common way you see it. Doesn't quite apply to controls very well because it requires like discrete moves and everything. But for this concept of a value function, and this is being the cheapest way to get home, I think it's helpful for that. Okay, so now we have the tools to solve time-varying LQR. Bellman's principle works on time-varying systems. Yes, it does. So if you look at this, the only thing that this changes is our time step here and here. So these time steps are specific to the value function. So our value function at time step k is different than our value function at time step k plus 1. So remember, the value function just tells me I give you a state. The value function will tell me how expensive it is to go from that state to the goal. Now, this is a function of time. So if this is like, the first time step or the 10th time step, that cost to go is going to be different. And for time varying systems, this is especially true. So if I want to generalize this to time varying systems, all I have to do is look back my derivation and see where do I have to accept that A and B may be changing over time. And it just means that like here's A, here's B. So these must be time specific. They must have a specific index for them. So with these things right here. And turns out that the only difference for this algorithm for finite horizon LQR and time varying LQR is, like I tried writing here, is that we can solve time varying LQR by adding AI, BI, and I'll do this in red. Actually, I'll do it even cleaner. I'll just say if so if we're doing time varying LQR, it just means that A is AI and B is BI, and then everything else is the same. So in your homework, you'll go through and you'll do this. You'll do a finite horizon problem and then a time varying problem. You'll use your Riccati recursion to do it. And the only difference is that we're going to plug in the A's and B's at those specific time steps. Sound good? All right, so now we're going to look at MPC, which is model predictive control. So what do we do when we have problems that don't quite fit in the LQR frame? So if it is LQR, we have a great solution for it. It's very easy, very fast, globally optimal for linear systems. And it just kind of works. It's amazing. But a lot of problems are not going to have this. And so basically, what do we do? What do we do if we have constraints or costs? So if I have various constraints and costs that don't show up in LQR, how am I going to solve those? And so this is where MPC comes in. So I'll give an example of a problem that we probably couldn't really solve with LQR that well. So let's write down our original problem. So this is our original problem. Now let's say I start adding stuff that doesn't quite work. So say I want to add, I want to add state constraints. So X for each time step must stay between some certain bounds. Have the same thing for U. I have control limits. All robots and actuators have control limits. And then say I want to, for the cost, say I want to add some weird, like the L1 norm of the third time step, you know? So I can add a bunch of weird costs and stuff. And this problem is still convex and easily solvable, but it's no longer LQR. And what that means is that I can't just get a nice feedback policy from this. It means I have to work a lot harder. And this is kind of where MPC comes in and uh, why we have all this specialized tooling. So the way MPC works is so LQR is just U equals negative KX. This is just a feedback policy. MPC is U equals so in LQR, I just have a nice little feedback policy. I take my X, multiply it by K, and I get my control input. For MPC, I'm going to solve a little traj-opt problem. So what I'm going to do is I'm going to say that X1 is my current time step. So if X1 so if X1 is my current time step, I'm going to form and solve this convex traj-opt problem. Now, it doesn't have to be convex, but MPC often is. We choose to make it convex just to make our lives easier because convex solvers, they work well without any babysitting. So it'll just work. We don't have to worry about the specifics. So convex MPC, super common. We'll use it all over this class. So convex MPC, if X1 is my current time step, I'm going to form this trajectory optimization problem. I'm going to solve for some n trajectory, and I can make this window whatever I want to. It could be, look 10 time steps forward. It could be look 100 time steps forward. And then I go and I grab this first control input. And return first control input. Let's go back to our 2D state space that we like looking at these things on. So I start right here. I'm going to solve, and this is our goal. So when I solve this convex traj-opt problem, it's going to give me a trajectory that gets me to the goal, or if that's what I constrain. So this is my MPC. But then when I go and execute this, what I'll see is that I'm actually going to move a little bit away from it. So where I move is going to be here. So in that first time step, I thought that I was going to move here, but I actually moved here because there's a little bit of model mismatch. There's unmodeled dynamics, noisy actuators. My state estimate is not that good. And all these things result in me moving a little bit off of where I thought I was going to. Just gives me a little bit of an error. So what do we do in MPC is that we just go ahead and replan. So we are going to just take from here, we're going to try and solve a new problem. And then this will keep going. So every step I take, my model is a little bit wrong. I end up going somewhere where I don't quite want to. So I have to form and resolve this problem at every time step. Now it seems super wasteful because I'm solving for a full trajectory. I'm only using the first input from this trajectory. And then from there, I'm just throwing everything else away and then resolving. And that seems like it's super wasteful and really expensive. And it is much more expensive than just doing LQR. But again, LQR can't handle all these constraints. So if I have actuator constraints, all these things that still make the problem itself solvable, just not with LQR, I can use MPC and do all of those. And you think about this in terms of like a conceptual understanding of what MPC is. You basically sit there. You have like if I was making like decisions every day in an MPC fashion, which is kind of what humans do, I sit there and I think to myself, like, what do I want? So I form my cost function. What are my constraints? What can and cannot do? And then I think like, how is like the world going to progress if I make certain decisions? And I'm going to plan some window in the future. So I'll have some N MPC window. Say I want to think about the next hour. I want to be like, okay, what can I do for the next hour? What are my constraints? And you go and you make that plan. And then in 20 minutes, I do the same thing again. I replan my full hour. So this idea of MPC is just you sit there and you, in a short horizon fashion, you plan out your next so-and-so time steps. You execute the first action. And then once you get there, then you replan because things have changed. I know more now than I used to. Maybe my cost function's a little bit different. Maybe I have new or old constraints. All these things can result in different MPC solves. And so this is at a very, very high level MPC. So what I'm going to do now is I'm going to use like a code example to kind of really make this clear. Because ultimately, it doesn't quite make sense until you've done it. So LQR is not open loop. LQR is closed loop. Closed loop just means that the function, the controller itself is responding to the state. So open loop is if I were to give you 100 control inputs and I say execute these sequentially, you execute U1, U2, U3, and you don't care what X's are. You don't take any feedback. So an open loop policy is just executing a bunch of U's. Any sort of policy that's closed loop is you execute a U and then you take in an X, and based on that X, then you make a new decision. So LQR is by definition closed loop because it's a function of X. I'm taking in the X. And MPC is also closed loop because I'm taking in the X as my new initial condition.
I see, but I guess what I mean is like the gain is not you're calculating all of the gains at the beginning, and then if there's any noise, you're not really accounting for that, right?
Exactly, yeah. And you actually don't have to. So in the case of just linear dynamics, and say that is truly correct, and I'm doing infinite horizon, finite horizon, doesn't matter about noise, it's actually still optimal. And this is the whole idea of like the certainty equivalence or the separation principle. Basically means that even with noise that we can't model, LQR is still the best we can do. And so Zach will go into this in the next few weeks, but this is like a pretty important distinction to make is that we don't really have to take into account the sort of noise that we're going to get when we build our controller for linear systems. For nonlinear system, all bets are off, and there's tons of examples where this like may or may not be true. But for linear systems and for LQR, we can design our LQR controller without any regard for what's going on noise-wise in the system.
Oh, okay, I see.
And then the next question is time horizon frequency for updating MPC more of a heuristic? Example, quadruped needs fast updates, but how fast? This is a really good point. So I guess there's two time things we're talking about here. One of them is the time horizon. So in my MPC problem, am I planning out 5 seconds into the future or 10 seconds or a minute or an hour? So time horizon itself is one thing you can tune. Obviously, the larger the time horizon, the more expensive it is to solve. So the shortest horizon we can get away with, the better. And if we can find some way to have our terminal cost capture our value function, then we can have an even shorter time horizon. The next thing is frequency. And frequency is also really, really important. So if the dynamics are very unstable, you really want to run this controller as fast as possible. So if it was a humanoid, you may want to run your MPC loop at like 300 hertz. If you're doing like a quadruped, maybe 50 hertz is appropriate. The frequency in which you run MPC is really dependent on how stable the system is and how, like, I guess, fast the dynamics are moving. And then your time horizon is going to be basically you want the longest horizon you can that you can solve in the amount of time that you have. And then you want that horizon to try and capture some of the, behavior that's going to happen. Does that answer your question? Cool. So now let's get into some code.
Kevin, sorry, one question on what you just said. When you said MPC should run 300 at 300 hertz, and this is because I have no background on this, but does that mean you run MPC 300 times every second, or?
Yes.
Okay, got it.
So yeah, I gave an example of if you had a very unstable system, you want to be able to react to the new states as fast as possible.
Got it.
So running this thing as fast, like 300 hertz, is like really ideal, even though it seems crazy. So let's do. Okay, so can we all see my Jupyter notebook right here? Cool. So the first thing is a linearization warm-up. I won't write this out because this has been written out a bunch of times, but again, I cannot overemphasize just how important this is. And you'll have to do this in your homework as well. And one of the reasons it's really important is because the way Zach does it in class, he will sometimes linearize in continuous time. So in class yesterday or on Tuesday, when he did the 2D or he did a planar quadrotor, he linearized that in continuous time. You don't, for the homework, you don't have to do that. We can just focus on discrete time. So the idea is that if I have xk plus 1 and f of x as my discrete time dynamics model, I introduce some delta notation. So x is just x bar u bar. X bar u bar is where I'm linearizing about. And then delta x and delta u, these are my deltas. So then I form my first order Taylor series, which gives me this right here. So here's our A matrix. Here's our B matrix. Now, if I substitute in our deltas, what I get is this, which reduces just down to this. And so what I've done is I've effectively recovered a linear model in these deltas from our original nonlinear system. And I went over this in the last recitation, and feel free to read through this and try and convince yourself. And then now we're going to do it for a nonlinear quadrotor. So I'll let you go through this on your own time, but there's two equivalent problems here. So the first one is, here's our normal LQR cost function tracking some reference X and reference U. And then I have a terminal cost. Then I have my initial condition. And I have my linearized dynamics constraints. So I just took my Taylor series, which is, it's linear in X and U, and I just shoved my Taylor series as the dynamics constraint. And then I have actuator constraints. And this is where LQR can't do this. So if I want to reason about the actuator limits of the quadrotor, I really have to use direct constraints in there. Otherwise, I'll get really weird, bad, potentially unstable behavior. So this is me including everything I want to for my little MPC problem, where I'm optimizing over X and U for a time step for a time horizon of n. Now, if I go and I substitute in, because you remember x equals x bar plus delta x, u equals u bar plus delta u. If I go substitute all these things in, you'll see that I get, the cost function is larger just because there's more terms, but now I'm minimizing over delta x and delta u. Now, the reason this is super important is because Zach in class will often just skip directly to this formulation. He will skip to delta x and delta u without really understanding what's going on. But if you follow this idea of start with the dynamics, then we introduce these delta variables, and then we go back to our dynamics and we just take a normal Taylor series, and then we substitute in our delta variables, we get a nice clean result right here. And then if I form our full MPC problem, we get this. But if I want to do it in terms of deltas, I get this. So understanding this full flow of how we got from discrete time dynamics, linearized dynamics, MPC problem with x's and u's, to MPC problem with delta x's and delta u's, that is super important to understand. And Zach will kind of whiz right by this, and he'll move directly to this right here without quite establishing the first three steps. So, and this will be in your homework too, but going over this document and like really understanding like what's happening is going to be critical to doing the homeworks well, I think. So both these problems are the exact same. I've written them both up in code. So, get Jacobians of our model. This is how we linearize it. And then here's our full MPC controller. And by full, I mean, I'll do full means solving for x's and u's. So I'm going to go ahead and I'm going to look at my n MPC window. So model is going to contain a bunch of parameters, params, our condition, our state at that current time step. And then this is just more indexing things. So I take in my state. Now it's time for me to solve my MPC problem. So I'm going to figure out where I linearized about, so x bar and u bar. And I'm going to get this for the specific window I'm looking for. So this is from the current index, IDX, to the current index plus nonlinear MPC window, n MPC window, -1. And so this is just going to grow and get the relevant slices of these trajectories that I want to reference on. Then I create my variables. Here I create my x. Here I create my u. My cost function is just going to be tracking on xref and uref. So here's just a normal LQR cost where I'm tracking x reference, u reference. I have an initial condition constraint. This says that my current position must be equal to, at least in the MPC problem, must be equal to what my actual position is in the world. And then I linearize this. I get my Jacobians about x bar, u bar. And then I go, and this is my first order Taylor series right here. And then I solve this problem. I get the value of u, and I return the first control input. And now equivalently, and so this, what I just wrote is me setting up and solving this problem right here, and then returning the first control input. Now the second problem is delta x's and delta u's. And like I said, Zach likes using these, and these are generally more common. And so here we see it's super, super similar. So if I just go and I substitute, the definitions of what my deltas are into everything, I get the exact same problem, but now it's in terms of delta x and delta u. So here's my cost function. X is x bar plus delta x, u is u bar plus delta u, and I put in my normal cost function. And then I have an initial condition constraint. So this just says that x bar plus delta x, which is x, must be equal to our initial condition. Get our dynamics Jacobians. Again, we have so x bar delta x equals the nonlinear dynamics function, and then a delta x, b delta u. And what's super important here is that if the trajectory we linearize about is dynamically so if x bar and u bar is a dynamically feasible trajectory, and what that means is actually satisfies the dynamics, then you'll notice that this and this are identical. So we can just cancel these. If that's the case, we can cancel these. But what I've written out here is the most general form of MPC. I'm making no assumptions about what X bar and U bar are. They could be made up. They don't have to be dynamically feasible. But if they are, and they often are, then we can just remove these terms and things are a little bit simpler. And then we solve for a delta U, and then we return U1, which is U bar plus delta U bar, or U bar plus delta U. So here's how the controller looks in a loop. So I just go over some, state size, control size, simulation length, and then here are my cost terms. Here's my reference trajectory. So it's just, I'm referencing about just hovering. So and then here are the parameters that we care about for our quadrotor model, which don't worry about the specifics of the quadrotor model. And then this reference that we're trying to, or I won't call this reference. I'll just do trajectory that we linearize about. And here is track A. And then in our main sim, the way this works is that I'm going to, u sim I equals convex MPC controller for x sim I. And then I take a step with our real dynamics model. And so just to give you an idea of, this is going to run kind of slow because I haven't optimized anything. You can get this to run extremely fast, but this is just like an educational example. But here we have a quadrotor that's tracking this blue dot. So you can play around with this, understand like why I did certain things, and you can play around with the cost function. You can add different constraints. But what we did here is that we took a nonlinear system, which was the quadrotor. We made it track an arbitrary trajectory by linearizing it about a different trajectory. And everything in this example is shown in ultimate generality. So there's no, I guess I did not use any assumptions to eliminate complexity. I put everything in there. And then what you can do when it's time for you to implement these things is you will recognize that there's certain areas where you don't need to do certain things. And the most poignant example of this is here. So you will see Zach in class all the time just say delta xk plus 1 equals a times delta x plus b times delta u. And this is really only true when the trajectory that we linearized about or the point that we linearized about was dynamically feasible. And by dynamically feasible means it respects the true nonlinear dynamics. But what I wrote out here was just in a general case. It does not have to be a feasible trajectory. It can be anything. I'm just writing out the first order Taylor series of this. So yeah, what you'll do in your homework is super similar. You'll do it on a linear system, so it's actually a little easier than this. But I just wanted to show this because I feel like the linearization is such an important step that is often kind of glossed over. And getting experience with it, tracking just a random figure 8 is super nice. So yeah, any questions?